To summarize, what we just showed in the previous slides is the result that gamma phi CL is given by the first term. The first term is given by it's given by an expansion where the first term is quadratic, and that's given by del 2 gamma phi CL del phi CL x1 del phi CL x2 at 0 times phi CL x1 phi CL x2 integration over x1 and x2. Then higher order terms where we are using the result that gamma phi CL at 0 is 0 and del gamma phi CL del phi CL at 0 is equal to 0. So that okay, so 0 here represents the extremization of gamma. If it's a Lorentz invariant vacuum, so gamma will have an effective potential, and in the Lorentz, if it's a Lorentz invariant vacuum, this 0 corresponds to an extremum of that potential. You can consider effective potential only for Lorentz invariant vacua, because only for Lorentz invariant vacua you will have the extremum will be a constant phi CL, and therefore you can ignore the derivative terms. So only the non-derivative piece of gamma, which is the negative of effective potential, it will be a solution of the extremum of that potential. And then you choose one of those extrema, and you set the origin of phi CL there at that point, and gamma phi CL at that point is also 0. That is how gamma is constructed, and that is why if you view this as a Taylor series expansion around phi CL equal to 0, then the first and second terms are absent. This starts with the quadratic piece, and then there are cubic and higher order terms. Now, as I mentioned earlier, these calculations can be generalized to non-constant vacuum, non-Lorentz invariant vacuum. You can, in that case, all the derivatives of gamma will be derivatives of phi CL in gamma should also be important. So therefore you are looking for the extremum of gamma, not only the effective potential. And so if you find an extremum of gamma which has a non-trivial profile, then you can define phi CL as a difference from that classical solution, and then it is not a classical solution. It's a solution of it's an extremum of gamma. It's not the classical action. It has the quantum corrections involved in it. So in that case also you can write down these expressions, except that 0 corresponds to a phi CL 0, which corresponds to j equal to 0, which corresponds to j equal to 0, but this doesn't have to be a constant. It can depend on background. I mean, there is a non-trivial solution here. Then also you can write these equations, but for our explicit demonstrations, we have been considering only Lorentz invariant vacuum. So there are many expressions which are more general than what we actually demonstrate here. Whenever I make any conclusion from the explicit Feynman diagram calculations of phi cube theory that we have done, those are only relevant for constant or Lorentz invariant vacuum. But otherwise, this framework of effective action is more general. Now, question is that what are these higher order terms? So one can write the just like in this this is a second order term of a Taylor expansion. So the full Taylor expansion will look like sum over n equals 2 to infinity 1 over factorial n delta n gamma phi CL divided by d delta phi CL x1 delta phi CL xn at 0 phi CL x1 to phi CL xn x1 to xn. Now, what we want to demonstrate, what we would like to demonstrate is that these derivatives are nothing but gamma n x1 to xn that we defined earlier for all n greater than or equal to 3. So for n equal to 2, we have already calculated this particular thing, which is the inverse of connected Green's function, and the claim is that for n equal to 3 onward, these coefficients, Taylor expansion coefficients, are nothing but this gamma n that we defined earlier. Okay, so therefore one concludes that gamma phi CL is the generating functional for 1pi vertices. Okay, because of this particular form here. Now you remember that 1pi given this result, this is equal to this. These are 1pi vertices, and recall that each 1pi vertex started out with the primitive vertex. So recall that each 1pi vertex starts out with and higher order in. So this is lambda. Suppose this is endpoint equal to endpoint, and the corresponding to that minus IH bar lambda n. So what I mean by this equation is that your theory can be a phi cube theory, but then higher point 1pi will start with a primitive vertex. Is supposed to start with a primitive vertex, but lambda n for n greater than 3 is not present, so this will be 0, right? However, this is true. You can think of phi cube theory as the most general theory with all lambda n's such that the higher lambda n's are set to 0. So these couplings are 0. But in general, you can write this equation. It's a lambda. Yeah, lambda square means all sorts of lambda n's will be involved there. So it's a schematic way of writing it. So if you have a phi cube theory up to 3 for the 3-point function, it will be lambda 3 or minus g here. Therefore, what one can say is that this one is minus I h bar, as we by definition minus I h bar gamma n. This will be if you take a constant field configuration, all the derivatives in the effective action will be 0, and therefore this gamma n will receive contribution only from V effective. So contribution for constant field configurations only contribution from V effective, and this one is the classical. This is contribution of the classical action. Is the classical action with constant field configuration. It is just the potential, which is sum over n greater than or equal to 3 lambda n over factorial n phi to the power n. So therefore, at tree level, at the leading order, if you take away all the loops, so higher order in lambda square and also in h bar. So if you take away all the loops, then only the tree diagram is so it will be on the right hand side. Tree diagram will be left. On the left hand side, we have V effective, and therefore we have a V effective, and therefore what one can write is that this implies, because of this result, that this is the one PI effective action. This is the result coming from that fact, that one can write V effective as the classical potential plus higher order contributions coming from loops and so on. So therefore this justifies the name effective potential, because classically effective potential is same as the classical potential. Justifies the name effective potential. Now our goal will be to demonstrate this, and we will demonstrate. So let us write down this equation. Delta n gamma phi CL at 0 is nothing but gamma x1 to xn. So this is the equation, and we will demonstrate for n equal to 3 and 4, and once we go to 4, it will be clear how it has to be generalized to higher ends. That will be straightforward. So how to show for proof for n is equal to 3? So the question is how to do the proof for n equal to 3. One basic identity that one would use here is that use the following fact: del j of x, the derivative using the chain rule. We have done it earlier. Chain rule, it can be given by d phi cl y del jx del phi cl y. And this is dy 1 over I, because phi cl is 1 over I del j of z. So this is x and y, so this is so del to z del to z j divided by del jx del jy times del phi cl y. This, if you now set at j equal to 0, then this becomes the connected two-point function. This is at j equal to 0. This is same as gc2 x comma x minus y at j equal to 0. So therefore we have an identity that del I jx, okay, so you have so it should be, so g would require one more factor of I, so this is I times this. So this is minus integral g2 connected x comma y del phi cl y calculated at 0, but 0 means j equal to 0 and phi cl equal to 0. This is equal to 0. This is the identity that one can use. Now, where would I use it? You use it, apply this operator on the n equal to 2 equation. So n equal to, recall, for n equal to 2, we had an equation which says that gamma 2 and g2 are inverse of each other. So this is the equation. This equation, you see, this equation says that gamma 2 and g2 are inverse of each other, but this gamma 2 is this derivative. After calculating this derivative, you have to set phi cl equal to 0. Here also, after taking the derivatives, you have to take j equal to 0. But this equation, this is also, even at non-zero phi and j, these are inverse of each other. So you can take this equation, this is equal to minus h bar I h bar delta x minus y, and apply that differential operator that I just described on it. So let me call this as 1, this as 2. So apply 2 on integral dz del 2 z j I del jy I del jz del 2 gamma ICL ICLZ. Y minus W. Okay, if you apply this, you would get del I jx minus integral. Let me write du gc2 x comma u del phi cl u. This applied on dz del 2zj I del J. So you can calculate, you can apply this operator that we just showed to be 0. You can apply this operator on the equation at n equal to 2, which we discussed earlier, and then you should get 0. And then what that is 0, we haven't taken j equal to 0 or phi cl equal to 0 so far. Of course, this equation itself has been obtained from an equation where we set j equal to 0 and phi equal to 0. But here we haven't done that. So that's what enables us to take these derivatives. This is a derivative. If we set j equal to 0 here, we cannot take the derivative. So in order to take the derivative, we have to take this at non-zero j and non-zero phi cl for this derivative to act on this. And then after calculating the derivative, you calculate the entire thing at 0. After taking the derivatives, you calculate that at j equal to 0 and phi cl equal to 0. So evidently there are two terms. One is this acting on this, and the other will involve this acting on this. So let me write them down. This is become the first term will become third derivative. That is the second factor. Then calculate it at 0. The entire computation at after doing the calculation, you set j equal to 0 and phi cl equal to 0 minus integral dz du x comma u then this phi, so then this will act on that. So I'm writing this factor, then a third derivative for gamma. Equal to 0. Then one more trick that one uses is to convolute this entire equation with a factor of G2. So what I mean by that is some renaming is needed here. Okay, I will do that renaming and write that expression in the next part.